of x comma 0, and you get whatever you get. And then f of x comma successor y, you get whatever you get. And then you're like, okay, I know what h is. H is you pick out the third thing, right? Because h of xy is it's this plus 4, and you add 4 of it. So pick out the third thing, and you add 1 4 times. You're thinking, okay, I got h, right? So let me write something here. So I got h. And then you're thinking, what about g? G is 2x plus 3, but you know, everything has to be done programming from scratch. So you're thinking, what do you mean programming from scratch? Well, programming from scratch means you got to get this in terms of the initial functions and the basic operations of composition and primitive recursion. So you're thinking, oh, so, but I can't do that. Then you say, okay, I will use back the same trick. I didn't mean to cross that out. I mean to put it below. So I will use that same trick of saying G is function obtained from G1 and H1. And you're thinking, oh, and then you do your mumbo jumbo and you get G, and G is this ugly thing here. And this is the H. And now this is a complete program. Now I rushed it because today I have class, and I will go over this, you know, in a test if you like. But I can go over maybe a few minutes because I didn't want to spend too much time on this. But it's like you say, okay, I can't see instantly that this is primitive recursive, but I said G of 1 maps this, the G1 will be when you plug x equals 0. So the G1 will be G1 map this onto this, and the G1 will be when you plug in x equals 0. And then the H1 will be when you plug in, you know, S of y. So you say G of 0 is 3. The G of S of y is this. G of y plus 1, which is 2y plus 1 plus 3, which is 2y plus 3 plus 2, which is G of y plus 2. So you're thinking, okay, so what is G1? G1 is 3 successor. G1 is that constant. And what is H1? H1 is 2 successor of the second thing. But notice, right, H was 4 successor of the third thing out of 3. This H1 is, you know, 2 successors of the second thing out of 2. So you're thinking, oh, it changes. Yes. So these are the little things to tell you if you know what you're doing. Now, you're thinking, Professor, I can't do those stupid things you're doing. I don't like it. Well, then you shouldn't have taken this course. That's the only thing I can say. But if you look back, Lee, and you look back at the next test, and this is what one student was telling. He's like, wait, this is the same thing. 2x plus 3y. The other one was 3x plus 2y plus 2 or something like that. And he's like, this is the same thing. Then you look at another test. And you're like, hey, just pick a random test. You're thinking, okay, my God, this is the same thing. Then like I pick another one, say 215. You think 2x plus 4y plus... So you're thinking, oh, it's all the same. Well, yes, kind of. And sometimes the number 4 changes, right? Sometimes the number 4 is, you know, pick a random test here, like a little more complicated thing. And then in our recent test, the number 4 was, let's see what our number 4 was. That test is ugly, but it was this. Today, the last time, I was doing lots of things, and some of them were very short. So I want to repeat number 7, because it looks too easy. Number 6, example 6, was monos, and which I did in terms of pred, and you could see the final solution is this, and you're thinking, you know, Professor, that's complicated. Well, can you compare this to a program? A program usually is 100 lines, right? Minimum 50 lines when you do programming. This is 1 line, and you're thinking, yeah, but this is horrible. I don't like it. Well, I don't know. But basically what we did is we tried to express monos of x comma 0, and then we got x, and we see that's your g of x, monos of x comma s of y, and then we got that's h of x. And then you're thinking, okay, I got the g, so g is just x, which is 1, 1, right? So put 1, 1 here. And then h is predecessor of monos, but you can't just put pred, right? You got to say h is equal to pred, right, composed with I33. And then you're thinking, okay, instead of pred, this is not a built-in, you know, initial function or initial procedure. You got to put this whole piece here. You're thinking, oh, and then that little circle is that little circle, I333. So you just took this and you replace it by that. And then that's the whole answer. And I mean, I like this stuff because it's like, to me, it's not a pain. And you don't have to, you just literally take this and you chuck it in here and you're like, that's the program and that's done. Now, this one I like because this one is so easy. You want to switch X and Y. So you're thinking, okay, you want to change the input. Instead of saying X to the Y, you want to say Y to the X, right? X times Y is the same as Y times X in multiplication, so there is no need to change. But suppose you want to do X to the Y. And in our homework problems, we did X to the Y, because we couldn't do everything here. And that textbook asked that, and I did it for you in the solution. So you should, of course, check homework problems. And then you want to switch. So switch is a basic operation. And switch is so easy. All you do is you pick out the second, then you pick out the first, and you say, hey, put it in this order. And that's it. And so you're thinking, that's the program for switch? Yes, that's the whole program for switch. Now, I can erase this. And I can say, okay. The last guy I want to talk about primitive recursive is this sine function. So why do we need sine? Well, I like this function because it is tricky and also because it's important. Sine means you say, okay, these positive 1 means, you have a positive sign. So if you're greater than 0, you're positive. So that's 1. And if you're 0, you don't have any sign. You could be anything, so 0. And we don't deal with negative numbers. So we don't have to say minus. So you're thinking, okay, that's what you mean by sign. 1 if you're positive and 0 if you're 0. Correct. And then sign bar is kind of like the complement of sign. 1 minus sign, right? Or 1 minus, because we don't have minus here. 1 minus sign. So you're thinking, okay, 1 minus sign is 1 if you're 0 and 0 if you're strictly greater than 0. Now, how can we write these two guys as primitive recursive function? And so I do the same game again, but this one looks complicated. See, in all the others, they have a pattern and everything falls through. But this one looks complicated, right? But it's not. But because of it's so short, that's why it looks complicated. So you're thinking, okay, I'm not sure where these things are coming. Let me just check. Okay, I have some, whatever, email. So you're thinking, you have a function of 1 variable, and I will do what you do. I'll put sign of 0 and sign of successor of y. And then you're thinking, yeah, that's a good idea. So sign of 0 is 0. You're thinking, okay. And so this is your g. Right? And then this gives you your h. Right? So you're thinking, okay. Then you're thinking, well, g of what? Well, okay, sine, this is the y. So there is no x, so this is just g, constant. It's a function of 0 variables. So g maps n to the 0 onto n. And that is why I'm spending a little time with this, because it is, you're seeing it and then you're thinking, I don't know what you're doing there. Okay. And then the h is mapping, it is h of, there is no x, y, and sine of y. So you're thinking, oh, okay, this is, not like you have h of x, y, and monos of x, y. There is no x, so it will be y and just sine of y. Yeah, so h of sine of y, sign of y. So h is a function of 2 variables. Okay. And, I'm not telling you it's easy, but I'm not telling you it's hard either. So you're thinking, okay, what is sine of s of y, the successor of y? You got to write it as in terms of y and the sine of y. So you're thinking, it's just 1. If you're a successor, you're greater than 0, so it's 1. And then I got to express this 0 and this 1. So what is 0? G is just, this is g. You're thinking, g is the constant 0, which is a built-in function. You're like, what? G is 0. Then what is h? H is, you're thinking, I have to get 1. But you have to have 2 variables. So you say, okay, take your 2 variables, pick out the first one. Yeah, you could pick out the second one if you want, but pick out the first one, apply the z to it, right? and then apply a successor. So the z makes this, whatever that y is, this becomes z of that becomes 0. Then the successor makes it 1, and that's your h. And if you notice, it doesn't have any x and y and things like that. It just says, well, there is no x, y because there is no parameter, right? And you're thinking, but Professor, there was an x here. Well, I could have put y if you like, because this is to kind of tell you what the function is. But this x here is the parameter, and this y is the function in which you're doing the recursion, right? The variable in which you're doing the recursion. And this x here is a parameter. Sometimes you have x with an underline. You have more than one parameters. Sometimes you have no parameters. Here you have no parameters. So this is g, right? And so you would have said, well, Professor, why didn't you write it as sine of y? And, y equals 0. And then this is y like that, right? And I could have, but this is how the book does it, because this is how everybody defines function in terms of x. They don't define function in terms of y, right? And so that might be a little confusing, because you're thinking, but you were saying x is parameter, and here but I can use sine of, anything, sine of w, right? Because this is just telling you what the function is, right? So this is a dummy variable, but this x is a parameter, and this y is the recursion variable. So that's the point. This x is important and this y is important. But here you can put anything you want. And I only put x because the book put x. Same thing here. The book exact definition of the book's definition. And if I put something else, then it will confuse you maybe. Okay. So we got it. We wrote this, and in one step we got sine. You're thinking, that's it? Function obtained by primitive recursion. And this, yes. Now, same thing I do for 1. You're thinking, oh, for 1, when x equals 0, you get 1. So you said, okay, this is the g now. That's the g, right? And so that's the g. And what is 1? 1 is, there is no 1 as an initial function. But if you take the successor of 0, you get 1. You're thinking, okay, I got that. And then sine of successor of s of y is equal to 0. So remember, here is where you get the h coming in, the h. You're saying this has to be the h, and you want to produce 0, whatever you get. Whatever the y and whatever the sine bar of y, you say, I want to produce 0. So you're thinking, okay, you got your 2 input. Pick one out of the 2, the first one, and then apply the z to it, you get 0, and that's your h, and this is your g, and you're good. And so the hardest thing, it seems, for a student is to say, okay, now I get this. So that's why I saved this for last. And as I said, how do you master this stuff? You do homework and you look at old tests. And sometimes I don't bring this in the test. I bring something that you can mechanically do. F of xy. I bring something like f of xy, show that this function, or add of xy or whatever, is equal to, say, 4x plus 7y. And I can't put minus plus 3 or whatever. And you're thinking, okay, so you will do f of x comma 0, this is 4x plus 3, then f of x comma successor y. So you have a method. And you're thinking, okay, what is he testing here? He's testing if you understand recursion, and you can, you're not allowed to use plus here, or multiply, etc. You got to just go back and put everything in terms of the initial function. In the next question, which is what we're going to do after this, you are allowed to use add and monos and pred, because you're doing things like exponentiation. And so you're thinking, okay, I will do that later. So now, we now know what is primitive recursion. And it turns out that there are functions that we get that are not primitive recursion. So the first one of these was produced by a guy called Ackerman. He was a colleague of Hilbert, and the two of them were good friends, and they used to drink a lot together. No, I don't know that. I made it up. But, I mean, you go to Germany, you see, like, if you don't drink, you stand up. Everybody drinks. There are so many taverns or whatever, right? And so everybody drinks beer, at least. But, Ackerman, I don't know if he drinks or not. So most of the natural functions that we encounter in number theory are primitive recursive. In fact, it is very difficult to find a function from end to end, which is not primitive recursive. So how do we get this? Well, this is the first thing. Ackerman defined his function, right? A maps n squared onto n by simultaneous recursion. So not primitive, simultaneous recursion. So it's not defined by primitive recursion. And primitive recursion is what is called recursion on the last variable, the y. And it turns out that he defined his function deliberately because when he put f of x is equal to ax comma x, then this guy is not a primitive recursion. And the essence of this proof is to show that f of x grows faster than each primitive recursive function. So it can't be a primitive recursive function, because if you grow faster than every primitive recursive function, then strictly faster, then you got to grow faster than yourself, which is impossible. But it is way too complicated to include in these notes, and also way too complicated to include in even a textbook, right? So we can calculate, the Ackerman function for various values, and this thing is called diagonalization. You take the diagonal term axx, and then you get a new function f. Okay, so what is the definition of the function? Well, you do recursion on two variables, and this is complicated. So you said, hey, I will state a of x plus 1, y plus 1 as a comma, right? The a of x plus 1 comma y. So you're thinking, oh my God, wait, I don't understand the first step. All right. So you want to get a of x plus 1 comma y plus 1. So we will know y is the secondary variable. This. So you're thinking, I am going to define a of x plus 1 in terms of a of x, and then that. You're thinking, can you do that? Because that's a big number. Yes, you can do that. And then you're saying, okay, I am going to define a of x plus 1 when you reach 0, right? Because this could be 0 to start off you as a of x comma 1. And then you're like, okay, I understand that. And then when you want to start at 0 on y, because sooner or later this will get smaller and smaller, because let's say you go a of 5 plus 1, then you get 4. Then you define a of 3 plus 1 for 4, a of 2 plus 1, end up a of 0 plus 1, and then you end up with a of 0. And then this y will be bigger, but it's just y plus 1. So you're thinking, okay, you did that, but I don't understand. Okay, I agree, but that's the definition. How do you understand? You see some value, right? So here is an example. So a of 0 comma y is y plus 1 by part c. You're thinking, okay, so we know that. A of 1 comma 0. So you're thinking, okay, I'm going to have to define a of sort of like, okay, you want a of 0 comma 0? That's just 1. So you're thinking, okay, I see. Here is 0, here, sort of like 0 comma 0, right? And then 0 comma 1, right? And 0 comma 2, So put wrong thing around it. And you can keep going up. So you're thinking, oh, I will change color now, and I will get blue. Oh, this is 1, this is 2, this is 3. And then if you have 0 comma y, it will be y plus 1. And you're thinking, okay, y plus 1. So you're thinking, okay, I know all of this. Then you want a of 1 comma 0. So here is 1 comma 0. So let me go back to red. 1 comma 0. So 1 comma 0, here is that guy here. That guy here, 1 comma 0. Right? You're thinking, okay, according to my thing, that is a of 0 plus 1, which is a of 0 comma 1. And you're thinking, oh, that's 2. So let me put in 2 here. Right? Then you want a of 1 comma 1. Now, this is when it gets complicated. So you're thinking, okay, you have the definition here. A of 1 comma 1 is a of 0 plus 1 comma 0 plus 1, because I am writing it like this because I want to put it like this. Then you say, oh, according to that, this is a of 0. And then instead of y plus 1, I put y here. I reduce the y, and then I put x plus 1, right? Because I can't put x plus 1, y plus 1. If I do that, then it's circular definition, defining something in terms of itself. x is equal to x plus 1, which is nonsense, right? So I have to put something lower because that's a y plus 1. So I put an x here and then I put an a of this. So you're thinking this is a of 0 plus 1 comma 0, right? You're thinking, but what is a of 1 comma 0? So you're thinking that is a of 0 comma 2. You're thinking, okay, because I just showed that a of 1 comma 0 was 2 here. Oh, okay. And then you say, but what is a of 0 comma 2? You say it's 3. So you're thinking, oh, okay. I see. So the next guy here, that will be 3. And then this guy here will be 4. And you're thinking, okay, you just go 1, 2, 3 up to y plus 1. This will be 2, 3, 4 up to y plus 2. I have no problem with that. That is easy. Well, that's what you think. Wait till the next step, right? The problem is, that's because it can be shown a of 0 comma y is y plus 1, a of 1 comma y is y plus 2. But when it comes to a of 2 comma 0, that's when things get complicated, right? And I wouldn't waste my time going through all the details. A of 2 comma 1, right? 2 comma 0 is 3. So you start with 3 here. Then you go to 5, right? Then you go to 7. So you're thinking, okay, this is getting a little bit better. So in general, a of 2 comma y is 2y plus 3. And you're thinking, okay, that's not so bad, right? I mean, you go from y plus 1, y plus 2, to y plus 3. I can handle this. This is no biggie, right? And I didn't give you the details, but you can check it for yourself. Then you go a of 3 comma 0, and a of 3 comma 1, and a of 3 comma 2, and then you see a pattern. And you're like, oh my God, I got 2y plus 3, and then I got 2 to the y plus 3. This is going very fast. So this will start at 2 to the 0 plus 3 minus 3. So it will start at 5. And then 2 to the 1 plus 3, that is 2 to the 4 minus 3, that is 13. And then 2 to the, where is this guy? Where is the guy? Here. 2 to the 2 plus 3, 2 to the 5 minus 3, that's 29. You're thinking, oh my God, this guy is going to get crazy. 5, 13, 29. You're thinking, but I think I see a pattern here. 5 and 8, 13. 13 and 16, 29. 6, 29 and 32 is what? 30 and 20, 59. No, wait. 32 and 29, 9 and 2, 11, 61. And you're thinking, okay, I see the pattern is 61, right? That would be a of 3 comma y. And you're thinking, oh yeah, 2 to the, 3 plus 3 minus 3, 2 to the 6, which is 64, minus 3, 61. And then you can keep going like that. Now, when it comes to a to the 4 comma y, so, you saw what they did determine my thing. A of 4 comma 2, your internet is unstable. Okay, I heard that many times. It's not my fault. I don't know what to tell them. A of 4 comma 2 is actually 2 to the 2 to the 2 to the 4. So you're thinking, man, that's a huge number, right? And if you're thinking, what is 2 to the 4? 2 to the 4 is 16. And then 2 to the 16 is 655, 65,500 and something, 536. So it's 2 to the 65,536 minus 3. And that's just A4, comma 2. You're thinking, wait. You mean the third term here is 2, you can't even write it on the universe, on each atom, the observable universe, it's more than that. And then, as for A of 5 comma y, we can't even describe it. Right? Now, I have proven in Theorem 2 all of these formulas. But since I have to cut something short, I cut this proof, So I'm going to X out this proof because the idea of what are you expected to know, right? If you look at the review sheet, it says, oh, you need to know the definition of the Ackerman function. So you say, hey, okay, Ackerman function is that stupid thing here. I got to memorize that stupid thing. Oh, it's ugly. I don't like it. But that's the only thing you got to do, right? You don't have to prove anything, and you got to remember this. Okay, so let me just surround the thing by a nice red ink. You got to remember this theorem to say, can you give an example of a function that is not, this can come in the test. Give an example of a function that is not primitive recursive. And you say, hey, define A to be that and F to be this, then F is not. And then that's it. You don't have to prove anything. You don't have to do any calculation or whatever, because we are trying to make life easy for you. Why? Because it got cut out of the syllabus, right? But it is nice and it is interesting. That's why I put it and I didn't take it out. And it is hard, but I wanted to get to recursive function. So, so much for the Ackerman function. So as I said, the important thing it's like when I was going to school, the Ackerman function was like, we were spending hours and hours doing all these things and calculating A4,3 and A4,2 and trying to get A5,2 and 5,1, and then, suddenly the computer blew up, right? Because we were trying to use a primitive computer. So the idea is that these things grow very, very fast, but they start out slowly, like a gentle thing, and then it rises quickly. So, as I said, this is the important part. So study this for your exam, and I think that's in the review sheet. You have to know what Ackerman's function is, and you have to know an example of a primitive recursive of a function that is not primitive recursive, and that's all. All right, so I don't think that is too much, but this looks ugly, but that's my job to give you 1, 2 ugly things, because they want you to know that such thing exists, and the only way for you to know is to give an example. And so it's not so bad. And let's leave this topic. But as I said, all of these things need proof, so I proved it all there, and I'm going to skip all that proof. So let me put a word here, skip or whatever, skip. Theorem 2. Okay, so so much for that. Now let's go and do this. So what is okay? So before I go and do this, you notice in defining the Ackerman function, Ackerman did something that is called simultaneous recursion. And when he did that, everybody was like, "Oh, this is cool." So it turns out that you could talk about recursive function, and you can talk about simultaneous recursion. But simultaneous recursion has problems because sometimes the things are not working out, etc. So there is a better definition that is called mu recursion. And then once this came in, this I think came in with like 3 people, Cleany, Church, who was his advisor, and Godel, right? So once they came in, everybody says, oh, this is way better than this Ackerman's simultaneous recursion, because that has problem. You don't even know how to specify, those things clearly, but it can be specified now, right? But Ackerman just give an example. So now, what is this recursive function? So we can define a wider class of function than the primitive recursive function by using simultaneous recursion instead of primitive recursion. So again, what does primitive recursion mean? Primitive recursion means recursion on the last variable, right? Simultaneous means you can do it on more than one variable, right? And in the case with Ackerman function, I did it with the first, and the second was the only 2. But all the functions we obtain will be total functions, and it is not a nice class of functions. So in order to obtain partial functions, we need to introduce a new operation called minimization. And it turns out this, I actually happened to meet Cleany in 1990. He was an old guy. He was probably born in 1910 or something like that. So he was like 80-something years old. And I was talking to him, and, I had presented a paper, and he said, I am glad you considered partial functions, because that's these youngsters, nobody wants to present total functions. So I said, sir, I learned from the best. He said, who? I said, you, sir. So it is always good to meet the people who, did these things. I met him in Atlanta, Georgia. So he was very pleased that I did, partial functions instead of total functions, because everybody wants to do total functions, which are supposedly simpler but more complicated. So how do we get, right, this notion of mu recursive? Well, the idea is this. You take a function of n plus 1 variable, so let g maps n to n plus 1 be a total function, and then we can define a partial function f maps n to the n by putting f of x, smallest value of y, such that g of x comma y is equal to 0. Now, g of x comma y might be 0 for all y. In that case, you say it's undefined. So you're thinking, oh, okay. So let me show you the power of this, minimization. So here, x abbreviates x1 to xn as usual, and the function f is said to be obtained from g by minimization. Some people call it minimalization, but most books like my book or textbook says minimization. And we write f is equal to mu g comma 0. What is the 0 about? To remind you, it's g of x comma y equals 0. Now, the one thing I want to leave you in this course is that you never put g, x, and y in the program. So whenever you have a program in computer science, you write your program, and usually you name the variables or whatever, first input, second input, or whatever, how they teach you. But you don't put x and y. The reason for that is because that complicates everything, right? You just give instructions. And instead of saying x, you could say first input I1, 2, y, I2, 2. Or if you expect more variables, you expect more input, you put I1, 3 if you expect 3 input, right? So that is why every program has to say what are the things that you can input. And if you don't have the format of the input, then you're no good. All right, let me just put two quick things here, 18 and 30. And if anybody else is here, tell me. So one is here, 30 and 18. And everybody else is here, right? So I got everybody else. So I think it's okay. And don't worry, Jonathan. Good luck in your second test. Just do well. All is forgiven. As long as you do well, all is forgiven. And so the rest of the people I will read in case they pop up later. So now, let g of xy is equal to x minus 3y. Then I can get a function from this. G maps n squared onto n is a total function. So you're thinking, okay, yes, it is a function of two variables, x minus 3y, and it's good. And then you say, let f is equal to the smallest, value of mu g comma 0. That means the smallest value of, y, such that x minus 3y is equal to 0. So you're thinking, okay, let's calculate f of 4. F of 4 is smallest value of y, such that 4 minus 3y is equal to 0. So remember, f is a function of x. So I got to say f of x. So let me write this. But it's written here. F of x is this, but I don't want to write that. F of x, some people write it like this. Excuse me. I'm sorry. I don't know what's wrong. F of x is equal to mu y such that xy, f of xy, g of xy is equal to 0. So that is the longhand version. And this is the shorthand programming version. The programming version doesn't have any x and y. And that's why I hide this. So I am writing it here. F of 8, f of 4. Smallest y such that 4 minus 3y. So you want that y. Now, in the computer is a simple device. It just goes 4 minus 3 times 0, 4 minus 3 times 1, 4 minus 3 times 2. Okay, I got 0. So the smallest value that works, right? So again, I will put 4 minus 3 times 0. And this minus is minus, right? 4 monas, 3 times 1. You still are not, this is 4. 3 into 1. This is 1. And then you go 4 minus 3 into 2. And then you get 0. 4 minus 6 is 0. So what is the smallest value of y that makes it 0? 2. You're thinking, oh, that's how you got that 2. Yep, that's how I got it 2. And so a computer loves this kind of thing. It's like, I don't want any complicated formula. I just want to try 0, 1, 2, 3, 4. And as soon as I get something that you like, I will give you that. Same thing, 4 minus 8 minus 3y. So you do 3 ones 3. You start at 0. 3 0 0. 3 ones 3. 3 2 6. 3 is 9. It's like, okay, it's 3. F of 9. 9 minus 3 times 1. 9 minus 3 times 2. 9 minus 3 times 3. You're like, okay, it's 3 again. And you can do 25. 25 minus 3 times 8 is not reaching, is plus 1, but 25 minus 3 times 9. So the smallest value that works is 9. And you're thinking, okay, I get it. So this function, x minus 3y, g is this, and f produces this function. So what's the use of that function? Well, it's just a function. And when you think about it, you're thinking, you know what? I think I recognize this function. If you take 25 and you divide by 8 and you round up, you'll get 9. You take 30 and you divide by, 3 and you round up, you'll get 10. So you don't need to round up, it's already 10. You take 4, you divide by 3, you get 1 and 1/3, you round up, you get 2. So this GF is actually this function, ceiling function of x over 3. And it's the most important, sort of like real function, as opposed to just integers. So you're thinking you can take any real number and produce a natural number. Yep, that's it. So suppose we want to get, g of xy is x minus y plus 3y minus x. We want to get that. That's my g. And I want to know what the f does. So the f, it takes that and it says, okay, I want to know what is mu of g comma 0. So you like f of 0 is, 0 minus 3y equals 0. So remember, this minus is this is absolute value, so I do need to put that dot again. But this is what this is equal to, right? So if you're thinking, okay, 7, minus 3 absolute value, right? It's equal to 7 minus 3 plus 3 minus 7. But in this case, it's x minus 3y. So let me erase this before it confuses these. So I did f of 0, the 0 minus 3y, you get 0. F of 1 minus 3y, thinking f of 1 is undefined. Oh my God, because you can never get 0. Okay, let me show you why you can never get 0. Because it's absolute value, basically. Because it's this plus this. And both have to be 0, and both can't be 0. So it's like 1 minus 3y, that's, when you put y is equal to 0, it's 1 minus 0, it's 1. So it's not equal to 0. Then 1 minus 3, it's 2. Then 1 minus y equal to 1 minus 6 is minus 5. Absolute value is 5. And if you keep going, you see you will never get to 0. So this is undefined. This is undefined. But when you get to this, f of 3 is undefined. F of 3 is defined. It's like, okay, what is the smallest value? The smallest value is when y equal 1, because you plug in 0, you get 3 minus 0, which is 3. You plug in 1, you get 3 minus 3 times 1, which is 0, you get 0. You plug in 2, you get 3 minus 6, which is 3. So you're thinking, oh shucks, the only value that works is 1. And the only value that works here is 0. And so it turns out that this function is x over 3 if x is a multiple of 3, and it's undefined if x is not a multiple of 3. Because you can't get something to make it 0. You're thinking, oh, this is wicked. But that's the whole point. So now you have a function that is a partial function, and it gives you 1/3 the value when it's an integer, right? If x is a multiple of 3. And if it's not an integer, it says it's not defined. And so that's another thing. And so these two examples showed you how these things, so you're thinking, okay, I hate this stupid minimization thing or whatever, but how is it going to help me? Okay, you'll see in a second. A partial function is said to be recursive. Well, the correct name is mu recursive, because when you're thinking recursive, you're thinking, that's why I started using mu recursive, because you're thinking, do you mean primitive recursive or general recursive or simultaneous recursive? No, mu recursive, minimization. So minimization means it can be obtained from the initial functions by a finite number of applications of Cartesian products, composition, primitive recursions, and minimization. And you're thinking, oh, you get one more operation than primitive recursion, this. Right. And so like if I give you this function, f of x equals to x over 2, let f1 of x equals x over 2 be smallest integer greater than or equal to x over 2. Right? So you know that. That's called ceiling function. Why do we call it ceiling? Okay, here is like say 7 over 2. Right? So 3.5, 7 over 2. Okay, what is ceiling function? This is called the floor, 3, and ceiling is 4. And this is 3.5, and he's in between. So, you know, he looks like 3.3, so here is it. 3.5, right? Okay, so you're thinking, I see. You just put it on the number line, and the floor is the guy, that is the floor, and everybody lives in some apartment, and he lives in that apartment, and that is his ceiling, and this is his floor, right? And the ceiling function of 3, right, is 3. The floor function of 3 is 3. But if you are in between, you have a top and a bottom. But if you have like 3, the ceiling and the floor coincide. You're thinking, okay, that's a funny function, but it's okay. That's how it's defined. Now, I have to write a program, right, to get f1. So you're thinking, okay, let g of x equal to this. So you're thinking, how did you come up with this? Well, we don't know, but that's what programming is all about. It's called guess and check. So you're thinking, oh, yeah, you're right. You write some student program, and we base it on what we know before. And I base it on this thing here. So I saw this thing was like a multiple of 3 things. So I said, okay, I will use that. And I saw this one here too. This one is x minus 3y. We have some experience. We saw that produce this. So I'm thinking, I'm going to use x minus 2y. So we don't know. But we by experience, like programming, how do you get good at programming? You don't know. You just have to learn some basic programming, and then you basically modify, right? So you're thinking, okay. You said that g is, and then you do a dry run, and you said then g is a total function, and if you put f1 equals the smallest y such that mu of g comma y is equal to 0, that's what this means. Then f1 of x is mu smallest y such that g of xy equals 0, smallest y such that x minus 2y is equal to 0, and then this is, what is the smallest y for this which will work? If the y is less than x over 2, this will not be 0. But if the y is greater than or equal to x over 2, then that's this. It will work. You'll get 0. You're thinking, okay, now, this is this is what you would call in programming, you would say, I made a flow chart. I know what to do, right? But that is not the answer. That's just the G. So to get the program, you got to write what G is. So G is monos of x comma 2y. You're thinking, oh, monos of x comma y plus y. So you got to write the G in terms of the original, functions. So you're thinking, Lord help us. So it's monos of x. So you're thinking, what is x? X is the first input, monos of x comma y plus y, first input. Then you put add of I2 comma 2, that's the second thing y. And then second thing again y. So you have y, and x. And you're thinking, boy, this is ugly. No, well, it's ugly a little bit. But then you say, okay, f1 is mu g comma 0, and then you put what the g is like this. And then that's your whole program. And the 0 is the 0, and this is your program. So you just have to write a program for this G. And that's your solution. So that's exactly the fourth question in the exam. So you're thinking, wait, that's all you do? Yes. And I am giving you permission in question 4 to use monos, to use add, to use mult, because I don't want you to memorize add and monos and write a long program. You know, I'm saying, okay, I'm giving you this as built in, right? And you're thinking, that's all. So you just got to find this G and check that it works. Yes. Now, here's another one. You want 2x over 3. So the last time I gave you x over 2, and you want 2x over 3. So you're thinking, okay, professor, I want some way. So all you do is you say, okay, basically you want 2x over 3, right? Minus y is equal to 0. That's what you want. But the problem is 2x over 3 is not an integer, right? Because this could be an integer, like 2 2 is 4 over 3 is not an integer. So how do you come up with the G? So you say, oh, look, just cross multiply and make everything integer. 2x minus 3y. And that has to be equal to 0. And you're thinking, oh, okay, so this is what you take, you know, to be like, oh, yeah, 2x minus 3y. And then, but you don't know it will work, right? But I'm giving you the technique now. You're thinking, okay, let me make this thing a little nice and this dot here, because it doesn't look like a dot. But I want to make it a dot. Okay, so 2x over 3 minus y. So from this, you get to this. Because this doesn't make sense because this is fraction and you are dealing with whole numbers. So you say, okay, I will put this. And then you check. Mu y such that g of xy is equal to 0 is smallest y such that 2x minus 3y is equal to 0. Smallest y such that this is writing it in symbol, this is writing it in words. And then you're thinking, okay, what is the smallest y? It turns out to be exactly this 2x over 3. You're thinking, okay, therefore, I got the answer. No, not so fast. You got to write this G in terms of these stupid things. So you're thinking, but professor, you know, I don't like what you're doing. But, okay, the monos is the monos, that's the monos, 2x and 3y. So you need multiplication of 2 and multiplication of 3y, right? And there is another parenthesis there that I forgot to put. So I failed. Okay. Then you got to write this in terms of the initial function, this in terms of the initial function. You're thinking, okay, but can't you just put 2? No, 2 is not an initial function. Now, here is the point. The point is everything has to match. This is a function of 2 variables, and you pick out the x, the first variable, which is the x. This also has to be a function of 2 variables, and it has to produce 2. So you say, hey, pick out the x, or you could pick out the y if you like, but pick out the x, take this z and make it 0, and then take 2 successors, and you'll get 2. So this 2 is not really the number 2, it's a function of 2 variables, and this x is a function of 2 variables, which you pick up the x, because why? The g is a function of 2 variables. And that is why I said x is I 1, 2, and the y is I, so 2, 2. And then here you want 3y, you pick out the y. And then here you get 1, 3, you can either put z of x or z of y, and then you put 3 successors. And you're thinking, okay, that's 3. And that's the y. So that's why you get 3y. And that's the x. And that's 2. You're thinking, yeah, my 2 is no good. So I wanted to show you these things are easy if you know what is going on. So again, you have a very primitive programming language, and you're thinking, I hate this. Well, that's why I told you don't do theory of algorithms. But if you like it, you can see the relationship to programming. It's simple programming, but it's not easy. I'm not going to tell you it's easy. Okay, but it's not hard either. And so then you say, okay, I see what you mean. G is a function of 2 variables. That's the first variable, that's the second variable. I1, 1, 2, and I2, 2. Because 2 variables are the first out of the 2 and the second out of the 2. I could also put 2 here, right? Because it doesn't matter which one I pick. The z will make it 0, and then the 3 will make it 3. And you're thinking, okay, if you say so. And then I write out the whole thing, and I said, f2 is equal to mu g, 0. And then you write out what g is. G is this whole thing here. and then the 0 is the 0. And you're thinking, man, this thing is horrible, but no, look how short it is. No program is this short. So I hope you see that it is not so bad. And this is the kind of thing you're expected to do. And well, this one is a little bit too easy, but the next one is the kind of thing you will get. So example 3, not to rush it. So you're thinking, oh, this looks more complicated. You take the square root of x, and then you take the ceiling function of it. And it's like, Professor, why do you keep taking ceiling function, and why don't you take floor? Because floor is more complicated, right? Ceiling is good, so this thing is designed for ceiling. But we will do floor also, right? But floor comes at a higher price. So ceiling is ideal. It's easy to look up. It's harder to kind of, do the things on the bottom. So you're thinking again, okay, I know your trick. Square root of x minus y, I want that to be equal to 0. So what do you do? How do you multiply? So I said, okay, you can multiply, but you basically want to say square root of x, right? If this is equal to 0, that means square root of x is less than or equal to y. You're thinking, yeah. If the square root of x is less than or equal to y, when you do the monos, you'll get 0. And if it's equal to y, when you do the monos, you'll get 0. I say, yeah. And then you square both sides. X is less than or equal to y squared. You're thinking, because you can't square both sides here. You think, yeah. And so then you say, this is x minus y squared. And you say, oh, that's how you got your g. Yep. So I got this as my g. But you cannot be sure the g will work. So, okay, if you have square root of 2x, you just put 2x minus y squared. And that's how the exams are coming. 2x plus 1 or x squared plus 3, whatever. And, you have square root. And then when you do homework and you see the solution, you're thinking, look, I think I can do this. He's not so bad. It's doable. But if you say I hate it, then of course you can't do it. So don't hate it. Pretend you like it just for the rest of the semester. And then, but, there is like 15 people not here. Only 15 are here. So I guess 9 out of those dropped though. But still, some people are not here. 6. So those 6, I don't know what they will do. But, they are not trying even. Right? But they go, you got to come to class. So thank you guys for coming to class. And once you get a G, your life is finished. Well, I shouldn't say finished. Your half the story is there. But what are we testing in the exam? We are testing if you know to go from here to here. That's what we are testing. Because it's one thing to make a guess, right? And as I told you the tricks to how to get the G. So yeah, that is worth about 2 points or so. But the main thing is to do the manipulation to get this. Because that means you know programming, right? So I will do the manipulations again, right? So when you look at the manipulation, you say, hey, this is my x minus y. So this will be my f. Mu g of x comma y equals 0. So this is equal to the smallest y such that x minus, man, I am just having to, the 2 didn't write here. It's a 2x, there, I put it everywhere except I didn't put it here. Smallest y such that x minus y squared equals 0. And when it's in my notes, I know. It's just that, when you get old, you forget to write things. You think you wrote it. So I will fix it before I leave today. Then you're saying, okay, so you got everything, it works out, right? Because the smallest value of y is, if the y is strictly less than, the square root of x, it won't produce 0. As soon as the y is greater than or equal to the square root of x, and y is an integer, you will get 0. So that's the y you want. And so you're thinking, okay, this does the job. I'm done. No, you've got to write the g in terms of this monos business. So you're like, okay, monos of x comma mult of y and y. You're thinking, okay, I understand that because you're writing x as x and y squared as mult of y and y. And then what I don't like is, why do you keep going back to your I12? Well, the reason why I want to go to I12 is because you're not supposed to have x and y in the program. The program doesn't have any x and y. So you're saying, okay, your F3 is this. F3 is equal to mu g comma 0. And I got to write this x So you will need monas composed with, and that's your x here, right? I1, comma 2. You're thinking, oh, g is function. So this is the g of, x and y. So this is the first variable. This is second variable. That's why you put I1, comma 2. Yeah, that's the x. How about the malt? Malt is malt. It's a built-in function I'm giving you in the exam. But in general, you will have to write the malt from scratch, and you'll get a longer program. But I allow you to use it as a, module to make your life easy, right? So I say in number 4, you may use monas, malt, pred, add, etc. to make your life easy and your program short, right? So I give you, built-in function. Then you're like, I want y, comma y, malt of y, comma y. So this is your y, and this is your y, and you're thinking, oh, okay, that's y, comma y, but we don't have a comma, we have this and thing. So it produces a function of 2 variables, y, and then you multiply those two, and then you get y squared, and you're thinking, okay, and then you get a comma, and you got a 0 because it's always g, comma 0. So this 0 and this is the same 0. And the comma is the comma, and the whole thing from here to here is g. You're thinking, I think I can do that, right? Now, the only difference is you might get square root of 2x plus 1 or 3x plus 2 or whatever, right? And you're thinking, well, I think I can do that too, because instead of putting just x1, 2, I will have 3x plus 1, right? So when you look at the solution, you're like, I think I can do this. And so, again, this is programming problem. And I don't mean to say that it's easy, but I don't think it's beyond you. Because if you can do a 50 and 100 line program in C and C++, that's way harder than this, right? And the only way that is easy doing programming in computer class is if you copy from somebody, right? But if you don't copy, this you don't need to copy, you just kind of use common sense. All right, last guy, I guess, 3. Well, I got 2 more. Can I finish these 2 more, and then I will stop after this. If I can't finish, I won't rush it, because these things are tricky. Here, I want F4 is x over 2 is if x is an even integer, and undefined if x is an odd integer. So you're thinking, what do you do here? Well, again, you're thinking, I want to produce 0 when you are even. So if you're even, you put x minus 2y, and so you say x over 2, this is basically x minus x over 2, so the y will be x over 2, and then 2y minus, 2 times x over 2 minus x, and you add these two and you get 0. But as soon as x is odd, this will be not, one of these two will be non-zero. So you're thinking, how do you know that? Okay, I will show you. Okay, so let us say this is the g of x comma y, and you want the smallest value. So remember, this means x minus 2y, or x minus 2y, regular minus absolute value. It's the difference between, so absolute value means the difference between x and 2y, and you take, whatever it is, negative or positive, you take the absolute value to get a positive, non-negative integer. So you want the smallest y such that is so. So you're thinking now, okay, let's look at, say, x was equal to 5. You're thinking, okay, 5 minus 0 plus 2 times 0 minus 5. Okay, 5 minus 0 is 5. 5 minus 2 times 1, that's 3, plus, 2 times, 1 minus 5, that's 0, right? You're thinking, okay, let me write something. 5 minus, 5 minus 2 times 1, that's 3, plus 2 times 1 minus 5, and that is 0. This is 3, and this is 0. And 3 plus 0 is 3, so you didn't get 0. Then you go 5 minus 2 times 2, you get 1, and then that is 0. 5 minus 2 times 3, this is 5 minus 6, that is 0, because this is minus. And then 2 times, 3 minus 5, that is plus 1. And you're thinking, oh my God, I will never get 0 if you put 5. And that's the whole idea, that you get undefined. But if you are like, if x is 6, then you will get 3 as your answer. So you're thinking, okay, I got it. So once you got your G, your story is over. And so the hardest part is to get the correct G. And then once you get your G, you just write what G of xy is. G of xy is absolute value of x comma 2y, which is absolute value of I1 comma 2 x comma y. And you're thinking, okay, what is, 2y? 2y is take y and add y. And absolute value is ABS, and there is a program for that, right? Because if I don't give you, then you have to say x minus y plus y minus x, right? So it will be x minus 2y plus 2y minus x. But usually I give. And then the end product is that F4 is equal to mu g comma 0. You just write what g is. And g is this. And that's why I put exactly this here. You're thinking, this is not so bad. I can do that too. Okay, and it's a recursive partial function because abs and add are primitive recursive total function. And so, and by the way, in case you want to know what abs is, right, I'm writing it for you here. So some people are like, well, but Professor, I didn't see this before. Okay, abs is you take monas of I2 comma I1 2, that is y minus, x, and then you take monas of that, right? So monas, this means this part is x monas y, and this part is y monas x. And this is, absolute value, x minus y, x minus y, absolute value. That's why they call it absolute. Okay, so you're thinking, well, Professor, I saw something, but I didn't want to say anything, but hey, something is not right here. Why didn't you put, you put I2, comma 2, 1, comma 2. So this is basically like you're picking out the y, and you're picking out the x, and then you're saying apply the monas, right? And I didn't see you pick out the x and pick out the y. Well, I don't need to. X and y are given because this is absolute value of x comma y, right? X and y are given. But if you want to be pedantic, you could put monas, for these monas here. You could put monas of and then a small circle. Okay, let's erase this and write it nice. Monas small circle. After this, I'll stop. Monas small circle, and then you say, okay, pick out the first stupid thing, I1 comma 2, and then pick out the second stupid thing, I2 comma 2, and then enter that into the monas, and that will give you x monas y, right? But as I said, you don't need to do that. Why? You don't need to do that because the x and the y come pre-prepared. Abs means absolute, like add. Add means add of x plus y. Abs means add of x comma y. So this is the first input, and the second input, they are in the correct order. But the reason we have to do it here is because we've got to switch them. You're thinking, okay, you switch them because you want to put y here first, and then you want to put monas x. But this is x minus y, so you don't need to do this. You just can put it like that alone. I hope everybody sees that point, and then you're good. Now, I think I will stop here because let me just make a little note or whatever where I stop. The last one I want to get to is x to the 1/3. So this one again, you just put g of xy is x minus y to the 3. And then, so you just do the game here, but I will stop at example 4. So let me stop here and put a little line and say that's it. Here I stop.